Hello everyone, and today this video is for estimate option implied volatility, and this is one of the project for my course FinTech Data Analytics, and this one of the course in the CS school in Fordham University, and I'm Shuining Yuan. Okay, for this part we will discuss how to estimate implied volatility. And in the first part, we will use math method to estimate implied volatility. Like we will use Bisection, Brent, Muller-Bisection, Newton, Halley, and Reader. And then we will evaluate by MSE and efficient. And then we will draw the conclusion. And at the second part, we will use BAW to find the American option and then do the selective learning. In the selective learning, we will use some machine learning method like KNN and SVM and the random forest and some boosting and some DNN method. And why we use BAW to find option is because our whole data frame is downloaded from NASDAQ, and in that option data we don't know which one is Europe and which one is American option, so we need to find out. And in the first step, the Europe option is be already calculated by our professor Ham, and he used bisection to calculate the implied volatility and find the difference between the calculated volatility and the original volatility. And if the difference is less than 0.01, and we will think it is the Europe option. Yeah, because Europe option we can use Black-Scholes model to calculate it, so we use this method to get the Europe option. And we can know for the following method, the function is Black-Scholes model minus options price, and we want to find this options root. And all this 10 method is the math method to find the root, is not about the machine learning. So we can say here for the new Newton, the difference for the Newton and the new Newton is in the new Newton we use Brent method as building method for the initial point, because we know Newton method is sensitive about the initial point. So if the initial point is different, it will affect the result. So we use the Brent as a building method to find the initial point for the new Newton. And it's similar for the new Halley method. It's like we first use Brent method to calculate the initial point and then plug the initial point in the Halley to get a result. And then after we find the root, we will use something, these three measure to value the result is good or bad. It's like the first step is how many steps use this method to find the result. And next is the MSE, and the third is combine MSE and step. It's like if the MSE is higher, then the result is not that good. And also the ET is the step, the average step number. If the average step is higher, then that means you need more time, more step to find the root. The method is not that good. So let's talk about the method. The first one is the bisection method. Okay, this method is very simple. It's like you find the interval and use the interval to look out like this FA and multiply FB, and if the result, if the multiple result is less than 0, that means they are different signal, and that means the root is between the A1 and B1, and then we will use like C1 to equal the average of AB, and like here maybe it is the B2, like you can use FB2 to minor FB1 to see if this signal is smaller than 0, and that means if the signal is different between FB2 and FB1. So we can see from this picture the FB2 minus FB1 absolutely is well bigger than 0. So the next step will between the between the B2 and the A1. So let's do the loop to find the root. And this for the Brent method, and this method is combined with the bisection method with the AQI method. It's like you follow this formula to get the next point, and not just a simple average of the interval. And this Muller-Bisection method is similar like that. It's like you connect the Muller method and the bisection method. It is first use bisection method to do yes and no, and then you use Muller method to do the next step, and then do these two methods together to follow the loop to get the result. So we talk about this Muller method. This method is that your original function maybe look like the blue one, is something like this, and then you find the 3 point, and this 3 point different signal, like x1 you can see it match the blue point at here, and x2 at here, and x3 at here, and use this 3 point, only use this 3 point to draw the red line. And you can see this pinpoint is the red line's root with the x, right? And this is the next x1, x2, x3, and do the loop and then find the result. And this is the Newton method. This is very similar because a lot of people use that. It's like you give an interval point and then use the tangent to draw this blue line, and then you find the x1 point here, and then do the same thing to calculate the tan, and then draw to get this and then until find the root 1. And the last thing method is Halley. This method is come from the Taylor series. You have the Taylor formula here, and then you want to find the root, so the result is around 0. And then based the results on the result and calculate it, you can get this formula, and then you can calculate step by this. So based on what I told before, we get the result here. And we can see for the MSE, all the methods look very similar, except this Halley method is a little bit higher than others, but also same great. And this because how we find this Europe option is find by the bisection method to find this option. So maybe that's a reason why the others looks very good, because we use this method to find, and then the other method is like is like this Muller-Bisection method is a little bit have connection with the bisection method, so there looks all very great. And for this step, we can say the bisection method step is very high, but this new Halley method, the step is smaller, is just around 3.6, and then this Newton is good. And this makes sense because this new Halley and the new Newton, its initial point is already calculated by the Brent method, so the step is not that bigger than others. And then we get the efficiency. The efficiency, the result is combine the step and the MSE based on the formula I told before. So we can say if the efficiency is higher, that means the method is better than others. So we can say here the most bigger one is the new Halley method, and the second is new Newton, and the most smaller one is the bisection method. Yeah, so that is the result for this 10 method to compare to calculate the volatility, implied volatility. And for the second part, we need to find out the American option, and then use the American option to do the selective learning. Like we will do some KNN and the SVM and the random forest. So we need to use BAW to find out which one is the American option. And this method is kind of developed from the BS model, and then I get this. I reference this paper and get the formula, and then I write the code to find the American option. And after I just found around 600 option, so it's not much, especially when I separate to ITM and OTM. So we can see the result here, like I use the result to do the PCA, and for the red one is the call ITM, yellow one is the call OTM. We can see the ATM is less. It seems like I can't see it in this picture. And it's like the red, the yellow one, the core OTM is on the below, and the red one is on the above. And for this, the put option, the red one is the put ITM, the yellow is the put OTM. Same like the ITM is above and the OT1 is down, but it also like it mixed together. And I also did for the UMAP. So we can see here the core OTM is separated with others, but this part they are mixed together, and here the ITM is also separated with this, but this time, but here this part they are mixed together. And similar for the T-SNE, they are all I should say mixed together. And this parameter I used 500. I remember I used a very big numbers, so even use that big number, they also mix together. And then we can say after we find this American option, I use them to do the selective learning. And this learning, the ideas come from our professor Han. It is like now we have our whole data, our American option whole data, and then we split to the train and the test data, like 80% of train and 20% of test. Then we continue to split to train and test. This time we split the train data to the train and the train test. And then in this train, we will like use the KNN or the SVM or the random forest outboost, this kind of machine learning to predict the train test. And then we will compare result with the train test and then get the MSE, and then we will rank the MSE and find the top 10%, I mean the biggest top 10% MSE, and think there are bad guy. And after we find this bad guy in the test tree, I will use the NS near neighbor search to find a neighbor in the train and the test data. So I will find all bad guys in the whole data set. And then I will drop all the bad guy and then get the clean data. And I will do the machine learning for this clean data. It's like if you use KN to find the bad guy here, and then you use the same machine learning KN to do this clean data. And similar for other method, if you use SVM to find bad guy, then you do SVM for this clean data. And this is the selective learning. And this is the step for the 1, 2, 4. And also we have the step 5. It is adaptive learning. It's like you have this bad guy in test data. I mean, you find your bad guy in test data, right? But maybe it is dropped that data is too much, or you lost some information. So you also use this bad guy in test data to do the near neighbor search in the train clean data, and then you do the learning. And if we use selective learning plus adaptive learning, it is hierarchical learning. And the whole method is from our professor Ham, and I read a code to make it come true. And first we need to know that for the KN, it has a lot of parameter to calculate the distance. So we need to find which one we need to use. Like this is for the ITM and this for the OTM. And we can see for the ITM, the best method is this one and similar to the OTM. For this method, the MSE is the smallest one. And then similar for the SVM, we can say we use all the parameter, we calculated the MSE for all the parameter, and then we find the RBF is better than the linear, is better than the poly, is better than the sigmoid. Yeah, so we use RBF to for our SVM learning for the OTM and the ITM option. And also we do the similar thing for our DN. It's like first we use grand search CV to find the best parameter. We will know how many hide layer size and what the learning rate, and so we will use. And then we will use this parameter to do the DN to do the learning. And this is the result. The blue one is the MSE after selective learning for the ITM, and the green one is the original ITM, original MSE from the ITM. So you can see if the blue one less than the green one, that means the selective learning, our like by the KN, is helpful. And but like this one, if the blue one is higher than the green one, that means after your selective learning, after you use SVM method to do that learning, your MSE is higher than before. Yeah, so that means not helpful. And also for the OTM, the blue one is the MSE after selective learning for the OTM option, and the green one is original MSE for the OTM option. And similarly, if the blue one less than the green one, that means your selective learning, your machine learning is helpful or not. So we can see this conclusion in this graph directly. It's like the X bar is the original MSE and the Y bar is the MSE after selective learning. And this green line is the line Y equal X. So if the point is under this line, that means your selective learning is helpful. That will make MSE down. If the point is on this gray line, that means your selective learning is not helpful. And if the point is on the line, it's very similar for before your selective learning and after selective learning. So they look very similar. So it seems like this blue circle, it is the SVM method for the ITM, and this is the random forest for the ITM. So these 2 points seems above the gray line, so this 2 point is not, improved after your selective learning. But others, it looks good or similar, so the result is not that bad. Yeah, I think that's all my result. And I'm glad to, and feel free to email me if you have some question. Yeah, thank you. Bye.